So let's talk about the heat of vaporization and the heat of fusion. As you can see, the heat is increasing in this sample of water. So as the heat increases, you'll notice the temperature will also increase. And it'll go in like this kind of pattern. It's going to go to a certain point, and we're going to have a heat of fusion at this point. This point here, it's going to slope down. It's not going to rise. It's going to transform into a different shape, and you'll have a heat of fusion. So this is where intermolecular forces, they dominate. This is ice and water. Okay. So then, this is the solid. Again, keep in mind, this is the solid state. As the heat increases, it'll go from a solid to a gas. So heat of fusion is going to happen right here. Okay, that makes sense. It's ice and water. Then you increase the temperature, increase the heat. And in a slope, it'll go up, up, up. And the water is going to eventually become water and steam. You know, this is where intramolecular forces are weakened. This is why we have gases. This is why we have water, because the particles are all spread out. And then we have water and steam for a certain amount of point until we get to a heat of vaporization area in 500 cals per gram, where it all becomes steam. So no intramolecular forces are acting on this part. Once you have that settled, you can get a better idea of how this works. An easy way is you have ice, and then heat of formation, a heat of fusion, ice and water, then water, water and steam, and then steam. Not really much of a way to remember this, but I think it's just better if you just know exactly what's happening. Here, molecular forces are strongest. Where it gets to water and steam, it's weakened, and when it's just steam, it's the least amount of intramolecular forces. Here's a better diagram, actually, but it's not as detailed. You'll see it's solid. It's going to be a latent heat of fusion. It becomes a liquid, and then you have a heat of vaporization. It becomes a gas. So as you can see, the molecules, they spread out more and more. The bonds become weaker and they spread out. So here's an example of a boiling point diagram. So melting point, which is in kelvins, are in high red. Like here, you'll find that these things here have a higher melting point. You'll notice that a lot of these high melting point things, substances, tend to be have higher, I guess, atomic mass numbers, which makes sense because there's just more particles or dense particles inside them per the unit of space they're given.